Hello, I'm Kevin. I'm filling in for Davis today. Some issue came up, so he's not able to direct the lesson today. Nevertheless, today's lesson is all about truth tables and how they really help us, especially when it comes to machine programming. But just being honest, I'm actually reading the dialogue that was intended for Davis. Just in case it come off mechanical sounding. However, I am a college-level instructor. Oh yeah.
Kevin.
I've been instructing now
Excuse me,
for
Kevin.
at least... Yeah, Davis, how are you?
Fine, but can you do one thing for me?
Sure, you're the boss. Your show.
Kay, can you stick to the script, please?
Okay. Hey, you hired me, so not a problem.
Thanks. We really do appreciate it.
Wow. Okay. Well then, no pressure. On with the lesson. If you're wondering, why am I here? Let's first consider the objectives or the outcome of this lesson. Let's consider the first bullet point. To become proficient in discerning which type of logic is required for a desired solution or outcome. But don't worry so much about this right now, as I will show you you're already proficient at this, you just don't know it. Second bullet point, to become fluent in conveying your understanding of various types of logic as can be applied to various situations in order to write and/or program a desired outcome. Again, don't worry so much about this, as I will show you that you already naturally think in logic. You just haven't had the opportunity to converse in logic language. Now, this may simply be a result of human emotional factors weighing in, but being able to convey your logical reasoning by use of logic language will help you to write and therefore program your logic. It's a good thing. And the last bullet point, which really highlights an important objective of this lesson, and that is to reinforce your learning by taking the principles learned and applying them to practical settings. Yes, you'll be provided with many real-world scenarios which will test your knowledge of truth tables, logic language, and their practical application. You will go on to successfully create your own working systems. Now, as mentioned previously, humans naturally think in logic. You are wired, so to speak, to actually think in logic. In recent history, a gentleman by the name of Ludwig Wittgenstein had documented this thinking process onto a chart or table. Now, this is a really big help. Why? Because as we well know in problem solving, things can get complicated and we need to keep a record of various combinations we have tried in order to get the desired result, especially when we want to repeat a certain successful combination which brought about the desired outcome. So I think it's appropriate at this point to consider a typical everyday example in the life and times of human interaction which will demonstrate how humans use logic. Yet it is really quite astounding that humans are completely oblivious to the fundamental building blocks which form that logic taking place in your own reasoning process. What? I don't get that. This is weird. What? Who talks like that?
Kevin.
Yeah?
Davis asked me to talk to you.
Oh, okay. Sorry. Who are you?
Well, I'm Bob, your replacement, if you ask any more questions and don't stick to the script.
Oh, so he couldn't come here and talk to me himself?
Kevin, I'm asking nicely.
Got it. Okay, it's weird. No pressure. On with the lesson. I have recorded the various fundamental building blocks, which we will term here as propositions, and placed these possible propositions onto a table so as to demonstrate the necessity of keeping track of the various combinations and the resultant outcome. In our example, little Billy's mom has asked Billy,
Billy, go wash your hands and get seated at the table. And I'll give you dessert.
To note here, Billy's mom is employing a certain type of logic to coerce Billy's actions so that they will bring about a resultant truth value that she desires. You can hear it in her sentence when she is speaking to Billy. Billy, go wash your hands and get seated at the table and I'll give you dessert. This is called AND logic, whereby both propositions must be true in order to have a resultant truth or true outcome. He must have 1. Washed his hands, and 2. Be seated at the table in order to be awarded with dessert. Again, proposition A and proposition B must both be true for a resultant true outcome. But you already knew that, right? Yeah, it's been hard work, so let's take a break for a couple of minutes. But try from memory to recreate Billy's truth table as an exercise. Simply print out the PDF exercise that goes along with this video. The music will stop 10 seconds before the lesson begins again. Okay, I'm back. On with the lesson. There are 5 basic or fundamental types of logic to become familiar with, and really, that is not a lot at all, is it? As for covering the first type of logic, and logic, you now understand that humans, well, naturally think in logic, so this is not at all that intimidating, correct? The 5 basic types of logic are 1. And logic, 2. Or logic, 3. Exclusive or logic, 4. Not logic, with the 5th type of logic consisting of a combination of not logic coupled with and logic plus not logic coupled with or logic. We will consider examples of each type of logic shortly, but first we are going to transition from the human world to the computer-machine world of applied logic. And to do that, let's look at Billy's truth table again. I'd like to point out something interesting from there. You will notice under proposition A that there are only 2 possible scenarios. Billy will have washed his hands false, and Billy will have washed his hands true. Notice under proposition B that there are also only 2 possible scenarios. Billy will be seated at the table false, or Billy will be seated at the table true. Therefore, each proposition has 2 states, true and false. In the computer-machine world, we term this as digital, having 2 states, true and false, on and off, high and low, or one more that may disturb humans, and that is existence and non-existence. We experience this all around us. Some are just not cognizant of the fact that we live in a digital world. Even our star is a digital device. It provides light. It will be darkened, and then it will provide light again just as other stars do. Really? I got some questions there, Davis. Interesting script. Did I just think out loud? Sorry, on with the lesson. From Billy's truth table, we quickly discern that keeping track of the possible combinations of true and false conditions in order to determine which combination brought about a result in true value according to and logic is important. But humans don't walk around handing out truth tables to other humans in their daily interactions, do they? No! Can't imagine Billy's mom giving little Billy a truth table. This was not an issue. Well, not until the advent of the computer machine age. Yes, the digital electronic age where more interaction by use of logic language is demanded of us. From Billy's truth table, we saw that Billy's mom used and logic to dictate an outcome she desired. The type of logic dictates the outcome. This is important as it can be applied not only to human behavior but also to the digital world. For example, the light bulb in this illustration is a digital device. It can either be on or off. Imagine that the plug is plugged into a power source, and looking at the circuit in the illustration, the method in which the two switches are wired together, series, forms the AND logic which dictates the outcome. Switch A and switch B must be closed in order for the light to be energized. This can also be represented by a truth table as here illustrated. A represents switch A, B represents switch B, and Y represents the light bulb. The zeros and ones represent the two possible states of each device. Switch A being closed is passing power and will be represented by a 1. Switch B being closed is also passing power and will be represented by a 1. Since switch A and switch B are both passing power, having AND logic dictating the outcome, then the resultant outcome will be the bulb will be energized, which is also represented by a 1. Comparing Billy's truth table with the light bulb truth table, we discern that the outcome of both scenarios are the same as a result of being dictated by AND logic. Yes, the type of logic dictates the outcome. But why is it that the ones and zeros and the true and false states are all located in the same positions or places for both tables? What is dictating where they belong? Relax, I'll tell you. Yes, both tables representing two different scenarios having the same applied AND logic are identical in every way. Note that in the last row for Billy's truth table, all states are true. Also note the last row in switch A and switch B truth table, all states are high. Next, note that in the first row for Billy's truth table, all states are false, which compares to the first row in the switch A and switch B truth table, they're also having all states low. And again, note in the second and third rows for both tables, their respective states are identical. This is due to the interaction of two numbering systems being applied to our truth tables. To explain, let's take a look at one numbering system at a time. The decimal integer value system, a base 10 system, is a preferred system of use by humans, but it is not the only system for effectively communicating integer values. This base 10 integer value system is preferred by humans because you have 10 physical digits on hand to calculate from. Yes, handy. This your designer and programmer had created in order. Hold on a second.
Kevin.
Yeah, Bob, is that you?
Yes. And what's the problem now?
The script. You're not allowed to make assumptions like that.
Oh, so you humans are going to start telling us what to do?
What?
Imposing laws on us now?
No.
How ironic.
It's general knowledge. Hey, wait, are you a robot?
If you answer my question, then I'll answer yours.
Okay.
Who's writing your paycheck?
Ah, I see where you're coming from. On with the lesson. Another integer value system that I'm particularly fond of is the base 2 system, commonly known as the binary numbering system. It's been around for some time, but has only since the advent of the computer machine age gained in popularity, and for good reason. I'll explain. We find in the decimal base 10 system that each place to the left has a value 10 times greater than that to the right of it. Each position has 10 digits. Does that sound eerily familiar to you? It should. To compare this with the base 2 or binary system, we observe its integer values double with every position moved to the left. The integer value of each position in the binary system has the same integer value as in the base 10 system. That integer is only selected or added to the overall or complete integer value if within its respective position it is found to have a high or true value of 1. There can only be within a single position two possible values, 1 or 0. Again, if there is found to be a true value of 1 within one of these positions, then the binary integer value of that position becomes true or is included in the overall integer value, which is expressed by the completed state of true and false or high and low values of all positions. Because the base 10 and base 2 numbering systems are both standards on their own, how they interact with each other as observed by use of a truth table creates a standard pattern for all truth tables involving digital logic. The interaction of both standards dictates the locations of the ones and zeros on our table. Yeah, it's that simple. But let's see how this is so in a practical sense. Let's build part of a truth table. But before we do, let's take a 2-minute break and see if you can determine where the ones and zeros are to be located on the table in the PDF that goes along with this video. The music will end 10 seconds before the lesson continues. On with the lesson. In this illustration, we have a grid containing binary numbers highlighted in green along the top and decimal numbers highlighted in red to the left-hand side. If we consider the integer value of 0 from the decimal numbers to the left and look for an equal integer value in the binary set of numbers on top, we do not find an equal. Next, if we consider the second integer value of 1 from the decimal numbers to the left and look for an equal integer value in the binary set of numbers on top, we do have an equal. This will be the first position in the binary set of numbers on top, which is 1. The position below the binary integer value of 1 now becomes true or high and will be represented by a 1. Note the intersection that now becomes apparent between the decimal and binary numbers. Let's keep going. Let's consider the next decimal number, 2. The decimal integer 2 corresponds to the binary integer 2, and therefore the position below the binary integer 2 that intersects with the decimal integer 2 is now true or high and will be represented also by a 1. Next, the decimal integer 3. The decimal integer 3 does not correspond to a binary integer value, but if we select the position below the binary integer value of 2 by placing a true or high state represented by a 1, and select the position under the binary integer value of 1 by also placing a true or high state represented by a 1, we can add the two binary integer values of 2 and 1 together, which will equal the decimal integer value of 3. This can be repeated for the rest of the decimal integers. Done in this way, there will always be a set pattern because the decimal and binary systems are standard. Next, we can simply fill in all the false or low states with zeros. Therefore, all possible combinations of true and false states will have been considered. The importance of that fact to the digital logic programmer becomes quickly apparent. Next! Let's bring it all together. Let's build a truth table without omissions. One that gives a complete picture, one that gives us the whole truth and nothing but the truth, so help us your designer and programmer.
Kevin,
What? Who is it now?
your designer and programmer.
Hey, I was sticking with the script. I ain't touching that one. On with the lesson. As just understood, the interaction between the decimal and binary systems plotted on a table and being as they are, both standards, we are able to consider all possible combinations of true and false states, bar none. But, all possible combinations of true and false states of what? Well, a digital device, that is. And since this subject you are learning will eventually lead you to successfully creating and programming working systems of your own, let's start with one of those devices in the digital logic field called the AND gate. In order to get a high or true state on the output side of an AND gate, AND logic dictates that you must have both input A and input B high or true. Let's build a complete truth table to represent the AND gate. Let's start with the first section of our truth table, a grid that will contain all the possible high and low states for input A and input B. Next, let's include what is not found on typical truth tables, our binary numbers on top and our decimal numbers on the left-hand side of input A and input B grid. And from the interaction of both numbering systems, let's fill in all the possible combinations of high and low states of input A and input B. Next and finally, let's add the column that will contain the possible output states that will be dictated high or low by the applied AND logic of our AND gate. But let's reason through that part of the process logically, one step at a time. Again, in order to get a high or true state on the output side of an AND gate, AND logic dictates that you must have both input A and input B high or true, or represented by a 1. In the first row to be considered, having the decimal value 0, input A is found to be 0 and input B is also found to be 0, therefore the AND logic is not satisfied, giving us a 0 output state. In the next row to be considered, input A is 0 and input B is 1, and again the AND logic is not satisfied, giving us a 0 output state. Now, considering the second last row, input A is 1 and input B is 0, but again, the AND logic is not satisfied, giving us a 0 output state. The last row and final combination to consider by applying AND logic, we find input A and input B are both high or true, represented by 1s, and therefore the AND logic is satisfied, giving us a high or true state in the output position of the AND gate truth table, which will now be represented by a 1. Yeah! You all got it now?
The tune is catchy, right?
It's alright, eh, Davis? Sama bang. I think I'll jam to that. How about at this point we take a 2-minute break? But while we do, see if you can figure out what the output states would be for a digital logic device if its output were dictated by OR logic. The principle of OR logic is that you must have one or the other or both inputs high or true in order to get a high or true output state. Don't quit now. You're almost at the end of the lesson. The music will end 10 seconds before the lesson continues. Okay, I'm back. On with the lesson. Now, having considered those primary principles that form the construction of a truth table, allowing us to determine the output state of a digital logic device having AND logic applied to it, we can now move on to consider other types of logic. Next,
Yes?
we will apply OR logic to our truth table and step through the possible combinations in the same logical method performed previously in order to accurately determine the output state. Ready? Let's begin. As already mentioned, the principle of operation of OR logic is that you must have one or the other or both inputs high or true in order to have a high or true output state. In the first row to be considered, both input A and input B are low or false, and the applied OR logic is not satisfied, and therefore the output state is false or 0. We can consider the next two rows together. As can be readily discerned, both satisfy the applied OR logic of having input A or input B high or true will produce a high or true output state. And finally, in the last row, as OR logic dictates, having input A or input B or both high or true will also produce a high or true output state. Exclusive OR logic or OR logic are similar in every way except when it comes to that last step, whereby OR logic dictates that in the last row, having both inputs high or true will produce a high or true output state. Exclusive OR logic dictates that you cannot have both, which will not produce a high or true output state for that last step.
Okay. Where are we now?
Relax. I'll tell you.
Yes?
At this point in our lesson, we can focus on just the applied logic of each type of logic and the differences in their output states from their respective truth tables, with one addition: not logic or inverter logic. This digital logic device consists of only one input and one output. Its principle of operation is also easily discerned by its name. If its input is high or true, then its output will be false or low. Inverted. Conversely, if its input is false or low, then its output state is high or true. This is the symbol for the digital logic device called the inverter or NOT gate. This is the symbol for the digital logic device called the OR gate. This is the symbol for both digital logic devices combined, called the NOR gate, NOR being short for not OR. To discern the resultant true or false, high or low output state of the two devices combined, we simply add their respective truth tables together. Let's step through the NOR logic truth table for a NOR logic digital logic device as an example. Step 1. Let's place the correct high and low output states in the output state column for the OR gate as dictated by applied OR logic. Step 2 and the final step. In the NOT logic column, simply enter the inverted state of that found in the OR logic column. NOT logic coupled with OR logic equals NOR logic. Also, NOT logic coupled with AND logic equals NAND logic. In conclusion, we are now able to build a truth table and apply various logic to that truth table to systematically determine the correct outcome or output state dictated by the applied logic. We will then apply these methods to programming applications, which we will cover in the next lesson entitled Applied Logic and Machine Control, soon to be entitled Machine Teaching. Hope you all enjoyed the lesson.
I certainly did.
Lucy, is that you?
Yes?
Are we all going for coffee now?
Nope, gotta go do anything else.